Okay, so this is the 8D handout. Um, and so let's take a look at what we got here. So in the first one, um, we've got a triangle to start with. It's got a 15 on this side and an angle of 45 and an angle of 90. So if you solve for the missing angle, it ends up being 45 degrees. So really what we got right here is a 45, 45, 90 triangle. And remember in the last lesson, the 8C lesson, we learned that a basic 45, 45, 90 triangle, that's a terrible hypotenuse, 45, 45, 90, has the sides, the isosceles part is 1 and 1, and then the hypotenuse, if you use Pythag, is root 2. So in this triangle, the x goes with the root 2 the same way that the 15 goes with the 1. So I can set up a proportion here. 1 over 15 equals root 2 over x. And then when I cross multiply, I get x's, 15 root 2, and now I'm done. So there's x. So then this one is 15 root 2. And notice it's an isosceles triangle. This big one up here is isosceles because of the tick mark here and here. So then this other side is going to be 15 root 2. And then there's another thing to notice. We've got parallels here. So if this is 45, you can use that Z shape, the alternate interior angles, to get that this one's 45. And since it's isosceles, with these two sides being the same, this one also has to be 45, which makes this one down here 90. So if I draw another 45, 45, 90 triangle down here, here's my right angle. There's 45 and 45. The basic one is 1, 1, and root 2. So now I can set up a new proportion. The 15 root 2 right here goes with the 1 right there, the same way that the y goes with the root 2. So I'll set up, what did I just say? 15 root 2 goes with the 1, the same way that the y goes with the root 2. And so then when I cross multiply, I get y times 1, which is y, equals 15 root 2 times another root 2. Well, root 2 times root 2 is regular 2. So this is 15 times regular 2, which is 30. So there's y. Okay, in the next one, part B, it mentions an auxiliary line. Now typically you want to either extend lines that already exist or draw lines that are either parallel or perpendicular to lines that already exist. And often a good hint is to think about rectangles. So one place you could draw a rectangle would be right here. And if I do that, then I force these guys to be 90. And 135 minus 90 leaves 45 degrees right there. This would be 90, so this would have to be 45. So notice we got another 45, 45, 90 over here. Well, this side right here, since it's a rectangle and this is 12 right there, you know that this side's going to be 12. This part's going to be 14 down on the bottom because the top is 14. So let me draw in the basic 45, 45, 90. 1, 1, root 2, 45, 45. So then notice the 12 here is like the 1 there, and the y is like the root 2, so I can set up a proportion. 12 over 1 equals y over root 2, and then when I cross multiply, I get 12 root 2 equals y. Well, notice the 1 and the 1 are the same, so this side is going to have to be the same as that side. So this part is 12. X is the whole base. So x is just 14 plus 12. So x is going to be 26. Okay? Let's take a look at the next one. What do the following triples of numbers have in common? Okay, well, let's see. We got 3, 4, 5, and then 6, 8, 10. One thing to note is this row is 2 times the first row. And this row here would be, let's see, if I take the first row and I triple it, 3 times 3, 4 times 3, 5 times 3, it's 3 times the first row. And the next one's going to be 4 times the first row. So if there was a fifth row, it would be 5 times the first row, which would be, let's see here, 5 times 3 would be 15, and then 5 times 4 would be 20, and then 5 times 5 would be 25. If there was a sixth row, I'd multiply these guys by 6, so I'd get 18, 24, and 30. If you kept going, and I wanted the nth row, I would just take n times the first row. So I would get 3n, 4n, and 5n. Now, why is this here? Well, the reason this is here is the whole unit is on right triangles. So one of the theorems that works with right triangles is the Pythagorean Theorem. So if I were to take any row here and plug it in, I'll just do it with the first row. 3 squared plus 4 squared is going to be 9 plus 16. That is equal to 5 squared. So this 3, 4, 5 represents a right triangle, gives a right triangle, because it works in Pythag. Okay. Well, notice, so this is a right triangle. You could take any of these rows and plug them in. You'll get that it works in Pythag. So all of these are right triangles. Each row represents a right triangle. So this could be A, this could be B, this could be C. And since they're all multiples of the first row, all the triangles are similar to each other. Right? They're all just different proportionate sizes of each other. Okay. You can look for other patterns too, like this one, they always increase by 3 in this row. This one, they always increase by 4 in this row. This one, they always increase by 5 in this row. Another pattern would be these go up by 1, these go up by 2, these go up by 3, these go up by 4. So there are lots of different patterns in there that you can find. Okay, let's go on. So let's see. Sides of a right triangle have lengths of 3x, x plus 2, and 40, where 40 is the hypotenuse. Okay, so 40 is the hypotenuse, and then I'll call this side 3x, and this one is x plus 2. Find x, and then the side lengths of the triangle. Well, we already know one of the side lengths is 40. Okay, well, it's the whole unit's on right triangles, and the one theorem we know that always works with right triangles would be Pythag. So I'm going to square 3x, and then I'm going to square x plus 2, and then I'm going to square 40, and 40 is the hypotenuse, so that's my c. So remember, 3x times 3x is 9x squared. And then x plus 2 times x plus 2 squared, you have to FOIL it. You can't just say x squared plus 2 squared. So if I FOIL that out, I get x squared plus 2x plus another 2x plus 2 times 2 is 4. So let me write that over here. X squared plus 4x plus 4. And then 40 squared is 1600. So if I simplify this, I've got 9x squared plus x squared is 10x squared. And then I've got plus 4x. And then 4 minus 1600, if I bring this over, will be negative 1596 equals 0. Now, if you wanted, you could divide everything by 2 to make the numbers a little bit nicer, but I'm just going to use a calculator anyway. A is 10, B is 4, C is negative 1596, and then I'm going to plug into the Pythagorean Theorem. B squared minus 4AC all over 2A. And I'll call up the calculator here. Oh, let me restart it. Okay, so A is 10, so 10 store as A, and 4 store as B, and negative 1596 store as C. Okay, so let's plug that into Pythag. So I'll call up my fraction alpha f1, numerator over denominator, negative b plus the square root of b squared minus 4ac all over 2a. So one of the answers I get is x is 12.4348, so that rounds up to 5. And then the other one would be the minus version, so I'll just come back up here, cut and paste, and then switch that to a minus, and we end up with negative 12.835. But notice 3 times a negative number is still negative, so this one's not going to work, so it's got to be this one. So x is about 12.435. So my side lengths, I already have the 40. If I add 2 to x, I get 14.435. And if I triple x, well, I'll just come up here and cut that one out and paste it, times 3. That's about 37.3046, so about 305. Okay, so let's go on to 4. So in this one, it says the area of a square is 128. Find the length of a diagonal. Okay, so let me draw a square. And we know a square has 4 right angles. And we know that the sides of the square are all the same, but we don't know what the sides are, so I'm just going to call them x. And the area of a square is length times width, which is x times x. So the area is x squared, which we also know is 128. So then I can get the side length is root 128. Okay, so what I've got now is that I'll just erase these x's and put root 128 and root 128, which you could simplify if you wanted to, but I'm not going to yet. What we want is the length of a diagonal. I'll call that d for diagonal. Well, notice when I cut this one, it's an isosceles right triangle. So this has to be 45 and 45 with the 90 there. So while you could do Pythag, I want to use that 45, 45, 90 theorem. And if I set up the basic one right here, 45, 45, 90, I've got sides of 1, 1, and root 2. So when I match up my sides, I've got d goes with root 2 the same way that root 128 goes with 1, right? D goes with root 2 the same way that root 128 goes with 1. So when I cross multiply, I get d equals root 128 times root 2, which is actually root 256 if I multiply those two. And root 256 actually happens to be a nice number. It's 16. Okay, so number 5 says, can you, first it's really asking, can you even form the triangle with those 3 sides? If you can, do you get acute, right, or obtuse? So we need to really check a couple things here. To have a triangle that exists, you take the you want to check something. You want to check if sum of 2 shortest sides is greater than the longest side. And if that's true, then you have a triangle that exists. Right? That we learned a couple units ago. If the triangle does exist, then you plug it into Pythag. Right? And if it equals c squared, you know that it's a right triangle. And then if we ended up making c a little bit bigger, then we get this. And making c bigger actually forces that right angle to become an obtuse angle. And if c squared, if I made c a little bit smaller, then I get this. And that ends up forcing it to be an acute triangle. Only if the triangle exists. So really, this is what we check first, and then if it works, then we check which one of these 3 it falls into. So in the first one, the 2 shorter sides are 4 and 6, so 4 plus 6, is that greater than 8? Well, yeah, 10 is bigger than 8, so this triangle exists. So I'll say triangle exists, and then we plug them into Pythag. So 4 squared plus 6 squared, we're going to compare that to 8 squared. So 4 squared is 16. 6 squared is 36, so that's 16 plus 36, 52, which is less than 64. So a squared plus b squared is less than c squared, which makes this thing an obtuse triangle. In the next one, first we check if it exists. 1 plus 4, the two shorter sides. Is that greater than 6? No, right? This is not true. This is false. So the two short sides are not bigger than the long side, so the triangle doesn't exist. Does not exist. DNE, not possible. And then for the last one, 4 root 3, I don't know, let's get a ballpark estimate for what 4 root 3 is. Let me start this over again. So 4 root 3 is about 6.93-ish. So if I do 4 plus 4 root 3, those are the two short sides. I'm checking to see, is that bigger than 8? Right? Well, if I add 4 to 4 root 3, yeah, 10.9 is bigger than 8. So this works. So the two short sides add up to be longer than the third side. So this is going to be a triangle that can exist. So then we plug them into Pythag to see what happens. 4 squared plus, and then you have to square all of 4 root 3. And we're going to compare that to 8 squared. So you could do this on a calculator. You just have to remember to put the 4 root 3 in parentheses. But if we didn't use a calculator, 4 squared 16. 4 root 3 times 4 root 3, 4 root 3 squared. You multiply the 4s, and you multiply the root 3s. So 4 times 4 is 16. Root 3 times root 3 is just regular 3. And then we're comparing that to 64. Well, 16 plus, this turns out to be 48. That actually equals 64. So it turns out that a squared plus b squared equals c squared. So then we can say we get a right triangle out of this thing. Okay, so let's take a look at 6. So notice it's another one of these big right triangles chopped from the right angle into two smaller right triangles. So that's one where you can normally use the up-down theorem where you go like x over z equals z over y, or if you read it the other way, you could do y over z equals z over x. Remember, the up-down theorem always has to start on the longest hypotenuse side. But the problem with that is I don't know any of those things, so I can't just jump right into it. I can't even use Pythag on this triangle or this triangle because I don't know enough about the sides. But there's a hint that says, look at how PSR's sides match up with PSQ's sides. So let me draw those two triangles by themselves. PSR is the big triangle right here. Let's see, PSR. And this is 9 and 15. Those are the only sides I know. And then PQS, or PSQ, is this triangle here. And I've got a 9, an X, and a Z. And let me label it PQS. So, oh, and then there's a right angle here. So one other thing I can definitely match up is the angle P's are the same exact angle right here. So that's reflexive. Which means that these, and since the right angles already match up, we know that these angles match up too. The third angles have to match up. Well, so if I wanted to match up sides now, the 9 in the big triangle is between the one curve and the right angle, so that goes with x. And the 15 is between the 1 and 2 curves, that goes with the 9. So I can set up a proportion here, 9 over x, so this 9 over that x, equals this 15 over that 9. 15 over 9. So then if I cross multiply, I get 81 equals 15x. And then if I divide by 15, what is that going to be? Let's see. 81 divided by 15. Whoops. 5.4. So I now know that this is 5.4. Well, you can get y pretty easily. The whole thing's 15. So if I take away 5.4, this is 15 minus 5.4. That's going to be 9.6. Okay, so z you can get a couple different ways. You could get z by doing Pythag on this triangle right here. You could set up some sort of proportion if you wanted to, but you'd have to solve for this side first, which is a little annoying. The one that I want to practice is the up-down theorem, because now we know 5.4 over z will be z over y, which is 9.6. So I'll do it that way. 5.4 over z equals z over 9.6. And let's see, so z squared is going to be 5.4 times 9.6. So I already have 5.4 there, times 9.6. That's 51.84. And then if we take the square root of that number, 7.2. And there you go. So there's x, y, and z. Hope that helps a little bit, and I'll see you guys soon.